हाँ क्या हुआ अभी उसका नाम सुन के आए हो करोगे कैसे कोई क्लास तो अटेंड नहीं कर हेलो 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 यहाँ से हेलो हेलो okay so I mean those who are coming they may not I mean it may not be very helpful for them anyway right because they don't know anything anyway so let me finish this portion which is going to take probably about 20-25 minutes so we were looking at fountain codes so DNA fountain codes and I think I gave you an idea about basic idea about fountain codes I've just recalled that stuff okay so we were looking at this paper in the year 2017 uh, by Ehrlich on fountain codes. This is the reference. Paper appeared in Science. And the channel was, I'm just recalling from the last class, uh, having constraint code channel and the eraser channel. And we are discussing eraser channel. And as we know, fountain codes can be used Here, content codes are rateless, error correcting codes for eraser channels. And in particular, we are, I started looking at the encoding procedure of loopy transform. So again, I'm just recalling what is fountain code. So if there are K symbol file, which are going into the digital fountain, so K packets, each packet is of L bits. It is entering into the encoder, and output is droplets of L bits. And if you want to reconstruct the file, you just collect any K droplets and you will be able to reconstruct the file. It's a very beautiful concept, right, of fountain codes. Now, how do we do this encoding? So, as I mentioned last time, we actually looked at random bits. We generate random bits for the encoder, and then the output bits are based on clock cycle, and Tn is equal to linear combination of these, information packets randomly. Okay, so random linear combination. So this was the matrix idea. So we were looking at K by N matrix, so on. And remember, so this is an infinite matrix, which is a generator matrix for the fountain code, and each column represents, so wherever there is a 1, I'm taking those corresponding information packets, and then we are taking the linear combination, and these columns are generated randomly. So that this shaded area is, is basically represents the eraser. So if those packets are erased, in that case, we are left with a matrix of size K by N. Okay. Now, there are different cases. If N is less than K, then of course we cannot reconstruct the file. If N is equal to K, it's K by K matrix, then we look for, if the matrix is invertible, we will be able to decode the file, right? And third case, when N is K plus some is small excess packets. Okay, so all these three cases we looked at. And so in the last case, when N is greater than K, we try to figure out from this random matrix how to look at a K by K. So what is the probability of finding a K by K matrix which is invertible? Okay, so that you can do the decoding. Then I mentioned about this balls in bin exercise. So there are balls, so there are basically K bins. So normally, the generator matrix, you can think of it's like a sparse code where the number of ones are very less, okay, very few. And so, you can look at it as a graph. So in that graph, so that graph is only a sparse graph actually. So basically, if there are K bins and I throw balls independently at random, I looked at what are the possibilities. Okay. Okay, so I am coming back to be transform codes, LT codes. So how the encoder will work? Each packet Tn is produced from source packets S1, S2, Sk, capital K. So there are capital K source packets S1, S2, S3, Sk, and then I am producing Tn. How we are producing Tn? As follows. So we choose randomly degree Dn of the packets from the degree distribution rho of D. So this linear combination degree that we are choosing for the packets, this we are choosing randomly as per some distribution, some probability, discrete probability distribution. Okay, and this is the very, very crucial part. Actually, I will show you with an example that the decoding actually is the complexity of the decoding is almost linear. In the case when we are looking at this, we are choosing a specific probability distribution, okay, of this degree, right? And second, choose uniformly at random dn distinct input packets and set tn is. So basically, we are choosing that degree as per the probability distribution, right? And also, the packets are also randomly chosen, right? So there is basically two kind of these things are involved, randomness, right? And then we just tn encoding is bitwise sum modulo 2 of these dn packets, okay? Degree is randomly which degree we should choose at a given time, and information packets that we pick up are also picked randomly, right? So how do we do this? So actually we will use pseudo random number generation, right? You know that there we use Galois field linear feedback shift register to generate the pseudo random number, right? You know that generating a random number is a sin actually, right? So somebody has said that generating a random number is a sin from computers, right? So actually it's a very, very difficult thing. So that idea we are going to do. So now I'm going to look at a toy decoding example. So encoding you understood, right? For the Luby transform code, there are two randomness, right? So one is basically degree dn is chosen with respect to some discrete probability distribution rho of d. Okay. So basically, there are two kind of distributions which are mentioned in the Luby's paper. One is solitron ideal solitron distribution, and other one he called as a robust solitron distribution. So ideal solitron distribution, depending upon the requirements of the decoding procedure, and actually, although it's ideal, but in practice, we use two parameters C and delta to control the distribution. Okay, and so that is known as robust solitron, distribution. Okay, so accordingly, we choose this rho d. Okay, and the second thing is choose uniformly at random dn distinct packets, input packets, and then choose tn. The output is just bitwise sum. Okay, modulo 2. Okay, so now I think we are ready. Let me show you. So basically, one thing to observe, just observe one very important thing in the encoding procedure. The encoding procedure, so, or encoding operation defines a graph connecting encoded packets to source packet. And if the mean degree, this degree is very important, is significantly smaller than k, in that case, graph is sparse. So sparse means, look at the matrix, number of ones are very few. Mostly it's full of zeros. Okay, that is on a sparse matrix or sparse. The graph is sparse, right? So now let us look at the decoding procedure now. So basically, this is decoding is quite easy for sparse graph code. I will give you a specific example here. So decoder task is to recover S from T is equal to SG, where G is the matrix associated with graph. So task of the decoder is to recover S from T, right? S corresponding to the information packets, the source packets, right? So basically, source packets I am denoting S1, S2, S3, SK, and the encoded packets I am denoting with T1, T2, T3, and so on. So let me show you the message passing algorithm with the toy example. Okay. So in this picture, you can see that there are 3 source packets, S1, S2, S3, right? And 4 encoded packets. So these I am denoting T1, T2, T3, T4. So you can see that this is 1, 0, 1, 1, this line here. Okay. So this is the graph. In this toy example, there are three source packets and 4 encoded packets. I'm actually, for simplicity, I am assuming here that packet size is 1 bit only. Okay, so it's 0 and 1. But actually, in general, it's L bits. Okay, right? Now, I look at these T1, T2, T3, T4. So these are T1, T2, T4, which out of this, so normally this T1, T2, T3, T4 is I mean, they are called as check nodes. Out of these 4 nodes, which one is having only one edge? Out of T1, T2, T3, T4, which one is having only one edge? Hmm? How many edges are connected to T1? So T1 is, 1, T2 is 0, T3 is 1, T4 is 1, right? Which one has only one edge? T1, right? Because all other having, 3, 2, 1, 2, right? So T2 is having 3 edges, T3 is having 2 edges, and T4 is having 2 edges, right? So I look at check node T1, T2, T3, T4, and look which one has only single edge, connecting edge. Okay, T1. Then what I do, I replace this T1 bit. So I look at, because my task is to find out the values of S1, S2, S3, which are the source packets. Okay, these are the encoded packets that I received. So, right? I mean the received things T1, T2, T3, T4 check nodes, right? So then what I do, I take this one bit here at, I take one bit here, this one. Okay, so T1 is equal to 1, and I replace basically, S1 equal to T1 is equal to 1. So S1 becomes 1, you can see that here, right? First thing, okay, look at the check nodes, T1, T2, T3, T4, which one has degree 1 basically, right? And then you just replace S1 with the value of T1. Next, what you do, so basically I should say that first thing is that set sk is equal to tn. I am writing a general algo here. B add sk to all check nodes tn prime that are connected to sk. So tn prime is equal to plus sk. So what I am going to do here, I take this. So S1 I found 1. Now I am adding this 1 into, basically this place here and this place here. Okay. Basically, you can see that this 0 will become 1 here, right? Because I am adding 1 plus 1 plus 0 is 1, and 1 plus 1, and 1 plus 1 is 0, the last one. Okay, these are the new bits, the new check nodes. Okay, why only these two? Can anyone tell me why I'm only changing these 2 bits? Anyone in the class? Why only these 2 bits? Now, if you look at S1 is connected to which? T1 and sorry, uh, T1, T2 and T3. S1 is degree 3 connected to T1, T2 and sorry T4. T1, T2 and T4, right? Okay. So now this bit I have copied to S1. I have copied. After that, I don't require those edges. So, but S1 is connected to what? Second T2 and T4. So those bits I am changing. Okay. I'm just adding this to the corresponding those 2 bits where the SK is connected. Okay. Okay. So that's what we have done. And then we remove the edges of SK. So basically remove all the edges of S1. So we are left with this. Right? So this I have done for S1. So to just understand, we look at the first we look at the T1, T2, T3, T4, look at the check node which has degree 1, right? And then see it is connected to S1, right? So S1 basically, because we want first bit, so just copy T1 as S1. Now look at S1 is connected to what other check nodes, right? Other than this, because from where we copied the bit, for other 2 bits, I am adding this as value of S1. So I'm just complementing there, right? Because 1 is added, right? So we are left with this figure, and then I am removing the edges going from S1. So we are left with this, something like this, right? Same procedure we will repeat for next iteration for S2, right? So S2, you can see that which bit is basically which check node has degree 1 now? The last one, right? This one, right? So in that case, what I'm going to do, I do the repeat the same procedure, right? I'll copy this 0 bit to S2. So 0 is copied here, right? And then you add this to the other portion, right? So 0 is added. There is no change, obviously, right? 0 is added to what? Wherever is the S2 is connected. So S2 is connected to T2 and T4, right? So this I have already added. So 1 will be added here. So there is no change in this scenario. It's 1, 1, right? Then I do the same thing. So 2 bits I have decoded. Now I have to only left is S3, right? So again, and of course, now, so S2 job is done. So these 2 edges will be removed. So we are left with something like this, right? Okay. So now basically, which check node? I mean, both of them has degree 1 actually. You can take any one of them, copy it here. So basically, you are left with 101 and you remove everything. So S1, S2, S3 is decoded. Got it? This is a very simple toy example of message passing decoding. Okay, this is known as message passing to very powerful decoding mechanism actually. Just very simple toy example how it works actually, right? Okay, so you just look at, so basically in this decoding procedure, you can observe that we want check nodes of degree 1. So how do you ensure check nodes of degree 1? So this is ensured because of the degree distribution rho of D. How do you choose rho of D? That will ensure degree 1. So this is what is the key discovery of Luby. When he looked at this graph, he found out that robust solitron distribution will do the job for us. Okay, just make sure that, because if this degree 1 is not available, decoding will be a difficult task. You will not be able to decode, right? So I mean, it should start decoding and then it should proceed. More and more degree 1 things should be there in each step. In each iteration, there should be degree 1 check node should be available for the decoding, right? If that is not the case, it will be a difficult task, right? So I hope you understood. Any question about this? I hope you understood this decoding procedure of the fountain code. So this we know that S1 is 1, S2 is 0, and S3 is 1. Right. So we are done with this. Okay. So now, as I mentioned, as I look at the decoding, how do we ensure that at each iteration we have sufficient check nodes of degree 1 so that we can do the decoding? We should be able to start the decoding. And so in the first iteration, there should be degree 1 check node. And in the intermediate processes, we should have degree 1 check node. Otherwise, decoding will fail. Okay. And so that is, so the question is now, how do we design this parameter? So basically now, this thing, rho d, the degree distribution, how do we choose? That is what is the important thing. I will give you some idea here about this. Okay. So I should mention choice. I think rather than going into too many details, probably I should mention what is the choice here. So one observation I should mention with of the Doobie is that if the number of packets received is close to Shannon optimal K, and decoding is possible, the average degree of each packet must be at least log E base K. And the encoding decoding complexity of an LT code will be at least K times log E base K. I'm not going into too many details how to observe these things, but so Luby's observation is if we carefully choose this distribution, we can do this actually. So basically, the ideal solitron distribution that he has chosen is that rho 1 is equal to 1 by K and rho D is equal to 1 over D times D minus 1, or D is equal to 2, 3, and K. Once you choose this, okay, the required graph will have the property that once one check node has degree 1 at each iteration. Okay. This will ensure that at each iteration, I have in the graph, at each iteration, I have a check node of degree 1. Okay. But there are certain problems. This degree distribution poorly behaves in practice. You know, sometime, I mean, this is what he thought of. A few source nodes will have no connections at all, So there was problem in this, and also sometime, no degree 1 check node. By taking this ideal solitron distribution, he ran the simulation. He observed that basically sometime there is a problem. So how do we fix the problem? He took what is known as robust solitron distribution. So I'm going to describe robust solitron distribution. It has two parameters, C and delta. So it ensures the expected number of degree 1 check node is about S equivalent to C times log E base A times delta times root of K. So I'm not giving any proof of these things, but I'm just mentioning. So rather than 1 throughout the decoding process. And the parameter delta is a bound on the probability that the decoding fails to run to completion after a certain number K prime of packets have been received. Okay. So basically, now I am going to define that robust solitron distribution. He defined a positive function tau of d as S by K times 1 by D, for D is equal to 1 to K by S minus 1, S by K times log of S by delta, for D is equal to K by S, and 0 for D greater than K by S. Then a normalized function mu of D is used, which is rho of D plus tau of D divided by Z, where Z is summation over D of rho of D plus tau of D. Okay, so this is the robust solitron distribution that is used. So if you look at the paper of Fountain codes, they just mention this robust distribution and then you are done, right? So actually, okay, of course, for more details, you need to look at the Luby's paper, but I'm not discussing it. At least now I should tell you how the encoding procedure works here for the DNA Fountain codes actually. So I should mention that encoding algo. So there are three portions. First is pre-processing. Second is Luby transform. And third is screening. So you take a file, then you do tar zz. So you get file.tzz. You know tar zz, you make a tar ball and use a gzip command to compress it. So there is a compressed file so that the entropy of the file is more. Okay. Then you divide this into non-overlapping segments of size L bits. Okay, L bits. Okay. So any file, take source file, first you compress it, make a tar ball of it, which is taught you. I mean, you know the command tar minus cvf and so on. I hope you know the command if you are using Unix, right? So you have the Tor ball, and then you decompose into packets, right, of size L bits. Okay, so now in the paper they have taken L is equal to 256 bits, which is around 32 bytes, right? So basically, once you do this, then I am going to, so Luby transform, you remember what? There are two randomness, right? You choose the degree randomly and the source packet randomly, and then you take the linear combination, right? So basically, how many packets each time in each iteration, you choose certain degree, right? So based on that solitron distribution, right? Okay, and then you choose those packets, and then you choose the random packets. First, how many packets are required? That quantity is kind of random, and then how many, basically, so which source you will take, which packet, source packet you will take. That is also random, right? These two things are having random behavior, right? So that will ensure. Uh, so there you use LT transformation, right? And because of this solitron distribution, it makes sure that when you do the decoding, actually, you have this, check node of degree 1 in each iteration that is available to you, right? And then you do the screening. So after that, once the data is out of LT codes, then those bits you convert into ACGT by simply 00011011 into ACGT, direct mapping, 2 bits for each ACGT, right? Once you have this mapping, so you have a string of ACGT. Now you check for the two constraints, whether it is homopolymer, so any ACGT is repeated, or GC content is within 50% range, right? With that parameter, with CGC parameter control, so 0.5 plus minus CGC. So with these two constraints, so if these two, if the generated string is passing, that it passes the test, then you say it is valid sequence, otherwise it is invalid sequence. That is how you collect the DNA. So output is in the FASTA file format. FASTA file format is NCBS. NCBS, I think I've shown you earlier in the Secret of Life lecture that there are two kind of format: FASTA file format and NCBS. So NCBI file format, gene bank. So FASTA file format is generated. Output, I mean, they have implemented in Python actually. Also, those files you can directly send it to where? Machine for synthesizing the DNA, right? So the DNA will be there, right? So this is the key idea about DNA fountain code using LT codes. LT codes are not, I mean, they are obviously powerful code. So they are near optimal, rateless forward error correcting codes. Raptor codes are much more powerful. In the paper, they have written that they have not done the Raptor code things because it is patented, right? So there are patent issues, so that they have not used it. But otherwise, there is only one major drawback is still, despite of doing these things, and when they have done the experiment, I think they spent around $3.85 million. Okay, get a paper in science. Okay, so this is still very costly, but it's still, I mean, it is showing you that a powerful technique of fountain codes. So I think you can clearly see that there are many places where you can modify this procedure, right? For example, in the screening business, right? So maybe we can use the homopolymer map, which uh, which can actually convert strings to directly by using non-homopolymer map, right? So maybe the screening can be simplified, right? I mean, so I mean there are possibilities of modification anyway. So here is a picture. I'll show you. As you can see that binary file pre-processing, so make segments of L bits. Okay. So here in this case, they are showing it for 4 bits actually, right? Okay. And then you do the Luby transform, random selection, and do those things, add random seed and so on, droplet formation, and then convert into DNA and check whether it is valid or invalid sequence. And then you get the output as a oligos, right? So this is a very, I think it took us 4 or 5 lectures to actually explain only few basics, right? We can go into more details how to, why this, this distribution and so on. But I think this much is enough for you to at this page. So are you ready for the quiz or what? Okay, so So quiz we will take next class, right? But I am telling you this time it will be 40% weightage. Yes, I may keep that, I have done it once and it was remarkable. After that, many, generations remember that, right? So that may happen. Okay. Anyway, thank you very much.